Welcome, everybody. So this week we are going to finish up our discussion of rotational motion, and we will be taking the model for motion we built in Physics 211 and considering the energy side of this thing that I have over on the right, thinking about how energy and momentum are going to work for rotational systems. We're going to start in this video on the energy side of things. And actually, as you can see up here, the work energy theorem that we had back in 211 is still perfectly useful and valid. So we can still write down that the change in the system's total energy is going to be equal to the net work done on that system. The only thing that we really need to add here is that rolling or spinning objects can have some kinetic energy that is in addition to their translational kinetic energy. So I've got my trusty tennis ball here, right? Obviously, I can have a tennis ball which is moving back and forth or up and down, and it's got some kinetic energy as a result of that. I can also have the tennis ball rotate or spin, and it will then have some kinetic energy, even if it's not moving side to side, because all the little parts of the ball are moving in different directions. And of course, you can have both of those things if the ball is going to rotate and move. It's actually pretty straightforward to calculate rotational kinetic energy. We simply upgrade the translational kinetic energy expression. So instead of 1/2 mv squared, which is the expression for translational kinetic energy, we get 1/2 I omega squared, where I is the moment of inertia of the object, and omega is the angular velocity. And that's pretty much all that there is to it for rotational kinetic energy. One last thing that I will add about rotational energy is that you can have work which is done rotational. All right, so you can see here our original definition for work is the force times the displacement integrated over the whole region. We can, if we want, write a rotational version of this that would look something like, let's see, I'll write down the original one. So we've got, work is equal to the integral, which I'll need to get my pen out here, the integral of a force dotted with a displacement dx. We can write the analog of this rotationally, and it's still work that we get at the end. It's just work done by a torque instead of a force, as the integral of the torque dotted with the angular displacement, so d theta. And it works in all other respects exactly the same. All right, that is it for rotational energy.